cells originated on Earth at a time when there was no oxygen in the ambient atmosphere, or almost none. And then after that, we have on Wednesday of next week the second quiz, and is due on Wednesday, and then the review session is on Wednesday, where we cover no new material, but you guys can have that be about going over textbook problems or reviewing material or whatever you guys want. So please come prepared to ask questions. And then the first midterm is Friday, and it's worth 74 points, 72 points out of a total of 400. So you should have been able to go in and look at your quizzes and figure out, and it should tell you which ones, what the right answers are and what your answer was. Is that accurate? Everybody can do that? Okay. So the scores were quite good on the quiz. The average in the class was somewhere a little above 14 out of 16. So the most common grade was out of 18, 14 out of 18, so 7 out of 9 is the most common answer, most common score. There are some number of perfect scores, some 8s, and some 7 6s, and maybe a couple of 5s. So that was a good distribution, so let's keep it up. Yeah, any questions about any of the programmatic stuff, where we're going? Yes?
Is the quiz representative of what you think is important for the exam, or is it kind of just
It's like a snapshot. It's basically to make sure you're keeping up. Certainly the topics are representative. Online, so online there's a study guide now under, I think, this year's exams. It's not a comprehensive list of topics, so please don't look at that list and then come back to me after the exam and say, you asked me something that wasn't on that list. It's pretty close to comprehensive, but not, it probably doesn't have everything. Last year's exam is online. That's the best way to figure out what my exams are like. The only difference between last year's exam and this year's exam is this year's exam is shorter. Last year's exam was 100, this one's only 72. So I will not stretch it out to make it look, to condense 100 worth of points into 72. It'll be like 72 points, like the kinds of questions in the last exam. The answers of the last year's exam are also online. You might want to use the opportunity to practice an exam before looking at those answers. And the answers to the textbook problems of chapters 6 and 13 are also online. So, we're in the middle of chapter 13, and last time we talked about what I think of as one of the two most important principles of all of biochemistry, which is that cells have to keep their ATP levels far out of equilibrium with respect to the hydrolysis reaction that would form ADP and phosphate. In other words, that ATP reaction that forms ADP and phosphate, in the way we think of it, if we just think of it in terms of the chemistry, how much energy is in that high energy phosphate bond. We define that, as we talked about last term, in terms of the stability of the products that form after hydrolysis. So here are 3 reactions, not the ATP reactions, but 3 reactions that actually yield more free energy in the standard state than ATP hydrolysis does. And notice that, and this is phosphoenol pyruvate, phosphocreatine, 1,3-bisphosphoglycerate, first and the third are glycolytic reactions that we'll encounter on Friday. And these are all hydrolyses, right? So these are kind of like a comparative, it's like chemical comparisons of how much energy there is if you hydrolyze each of these high energy phosphate linkages. And the amount of energy that's in them, the delta G, right, this delta G is this with respect to the product. So really the high energy aspect of the bond is reflected in the stability of the products, which is why on this slide here, we commented that the high energy phosphate bond, which really means that the products are highly stabilized, meaning that they're low in energy so that the gap is big, right? So that you get a big delta G out of it, and if you get a big delta G out of it, then it's a high energy bond. And ATP has an intermediate level of energy that it comes out of hydrolyzing between the beta and gamma phosphates. Why not have ATP be the highest? Because ATP is serving as the cell's energy currency, and so if we want to make ATP, we need to have something that's higher than that in order to drive the unfavorable 30.5 kJ per mole that ATP synthesis costs in the standard state. Right? So there's got to be some reactions that are higher than that. Having said that, these sorts of reactions where you have, for example, a bisphosphorylated sugar that's a very high energy compound because of this acyl phosphate here, that is converted, that is used to make ATP in a coupled reaction, because this guy would yield, minus 60 and this guy is only plus 30, so it would be favorable. Right? You make ATP on the surface of the enzyme that does that. That's called substrate level phosphorylation. And that is one way to make ATP in cells, but it only makes about 5% of the total ATP in cells. The other 95% gets made by a process called oxidative phosphorylation, which I will say something about in a few minutes. Okay. So any questions so far about sort of the structural basis, what high energy phosphate bonds, high energy bonds mean, why ATP has a high energy bond, its function as the energy currency of the cell. We could look at this. This is nothing more than a table of these reactions, which include the ones we've already looked at biogenetically. So here's ATP going to ADP plus phosphate minus 30.5 kilojoules per mole. This is just kcal column here. Some numbers are higher than that, some numbers are lower than that. So one thing to notice on this table, the sugar phosphates are low. These guys are above, as diagrammed on the other slide. But here, we've got acetyl-CoA, which is a thioester. And it releases as much free energy in the standard state when you hydrolyze it, as does the ATP hydrolysis reaction. In fact, very slightly more, minus 31.4. And it turns out that acetyl-CoA, as we will find out soon, is a very important cofactor in intermediary metabolism. And so we could look now at what is it about acetyl-CoA that makes this a high energy bond. This is why it's used. And the way to really understand it is to think of the hydrolysis as a comparison with oxygen esters. So if this is acetyl-CoA, and you notice here there's this CoA part, and I'm hiding the structure of it because it would take up this whole slide, this big structure, which we will encounter soon. But the business end of it here is just thioester bond. Right? So this S goes on to make the rest of them off. If you hydrolyze a thioester bond, you get CoA and then sulfhydryl, and then you get acetic acid. Right? So that's hydrolysis of this thioester, just like before we had hydrolysis of acyl phosphates or phosphodiesters, and we got free energies of hydrolysis out of that, and we can classify things as high energy or not. And this one, when you do it, it does classify as high energy, minus 31.4. So acetic acid forms and hydrolyzes in this reaction. But this isn't really the reason why this is a high energy compound. So the way to understand it is to compare it to an oxygen ester. Okay? And the reason why the oxygen ester is not a high energy bond than the thioester is that the oxygen ester, as a substrate for the water, as a reactant with water that's going to be hydrolyzed, is itself stabilized because of this resonance. Right? So this oxygen in the oxygen ester can take on a partial negative charge, whereas the comparable sulfur in the thioester, sulfur is much less electronegative, doesn't take on a negative charge. Right? So this guy's up here, the oxygen ester is here. The hydrolysis in each case gives you pretty much the same products. This line indicates that the free energy of these products and these are pretty much the same. So this sulfhydryl and this oxygen, not much difference in the free energy of those two compounds. But the delta G is a lot bigger for this than for that. Right? So this kind of emphasizes that it's not only always about looking at the structure of the products. Sometimes if you're looking at these reactions and the molecule itself may have less energy in it than you might think, because it has the capacity to be stabilized. Right? Before we talked about the stabilization of the resonance stabilization of the products. Now we're talking about the resonance stabilization of the reactions. Okay? So that's why acetyl-CoA as a thioester is a common cofactor in enzymatic reactions. And it gives us another metabolic role for sulfur. I mean, sulfur is a very important element. It's only, I think, the 6th most abundant element in cells, but besides cysteine and methionine, it kind of infiltrates itself in lots of different other places in metabolism. This is a key one, right, inside of acetyl-CoA. Okay, so on this slide, I just want to emphasize the mechanism by which ATP can make its make the energy in its phosphate bond available is very different in different metabolic contexts of the cell. You guys talked about myosin and actin last term? Okay, so you know there's ATP hydrolysis there, right? There's no chemistry reaction coupled to it, like synthesis of a sugar phosphate in that case. What we're using ATP hydrolysis for is actually this physical motion of dragging these filaments, right, which requires physical force. Like it's like there's resistance, there's drag in the cell. You got to slide something, you got to break a bunch of weak interactions and form new ones as you slide one filament past another, right? If you're talking about moving in a microtubule, it's transporting cargo inside of a cell, that's another example. So there's a number of examples. Sometimes also the conformational change of a large macromolecular particle has to undergo this big change. When you learn about protein synthesis next term, you will find out that GTP is used in the way, just as if it were ATP, and it's used in aspects of the whole translation mechanism that have nothing to do with actual peptide bond synthesis, but everything to do with the way the ribosome has to go through these complicated gymnastics to get from one conformation to another, which costs energy. So some of the energy of protein synthesis has to do with moving the ribosome around, so to speak, the parts of it with respect to each other. So that's one way, kind of what I said here. And then another way would be something like what we've talked about already, where we have hexokinase